Okay, welcome everyone to the first of several distinguished speakers that we have in the Distinguished Speaker Series for the Center for Data and Computing this fall. My name is Nick Feemster. I'm a director of CDAC. I work in the area of computer networking, applications of machine learning, network measurement to network performance and security. If you want to learn more about that or about CDAC, I'm right down on the second floor in the corner over there, so please come visit. We're trying to make the space more cool and more inviting, and pretty soon there'll be not only fun people down there, but cool places to hang out. So what is CDAC? CDAC's mission basically is to basically be the nexus for data science research on campus. It's inherently an interdisciplinary center and aims to bring together different disciplines where the applications of machine learning and data science can catalyze new discoveries or create new breakthroughs. So the idea basically is enabling interdisciplinary research both in the discipline of data science and in the domain itself. There's a process by which research in this area is incubated through a seed grant program. I'll tell you about that in a second. We also do convenings, so if you have an idea for a workshop or some people that you'd like to get together in the area of data science, we are all ears. We facilitate those types of events. And the other thing that we do basically is bring together partners both in industry as well as groups across campus to work in interdisciplinary problems in the area of data science. More to come on that. I think you'll hear more about CDAC throughout the fall. I'm sure we'll have more exciting things to announce as we get going. But just one quick thing to announce is the call for discovery grants for autumn 2019 is out. You can see some of those details here. But the gist is essentially that there are two types of grants that we are giving. One is basically on collaborative research for cutting-edge research across domains. So you're supposed to basically have one PI in the data science, computer science realm, and one in another domain. It could be any other domain across campus. There is also going to be a proposers day, essentially a meet and greet. So if you're interested in or know about one area and you're looking for a partner for this, we are helping to facilitate that. There's also a part of the grant process that if you want to have a convening, there's an opportunity for that too. More about that on the website. Also, today we are lucky to have Fernando Pérez, who's going to give a great talk, and I'm going to introduce Mike in a second. But I also want to point you to the Proposers Day, which I just mentioned. That's coming up next week. So if you want to make friends and write a good seed grant, that's a good place to come hang out. Also, if you want to just meet us, we're fun people to talk to. We'll all be there. Also, next Friday, we're having a talk on application machine learning to network security from Microsoft. And then the following week, we'll have Alex Gray, who's the head of AI research at IBM, who will be our next distinguished speaker. For this talk, I would encourage you, if you have questions or if you're interested in what other questions people are asking, this talk is being live streamed and archived as well. But we are using a platform called Slido, did I say it right? To allow people to basically contribute questions, upvote questions, etc. And our communications director, Rob Mitchum, will be facilitating some of that Q&A. Without further ado, let me introduce Mike Franklin, who will introduce our speaker today.
Yes. One level of indirect.
Exactly.
Yeah. Good. So I'll be quick because we want to hear from Fernando. So Mike Franklin, I was, I guess, the founding director of CDAC. And so I was director when we had come up with the idea of having a Distinguished Speakers series. We said, OK, well, let's invite Fernando. And then we started wondering about who else we should invite. So it was like, if you're going to do a Distinguished Speaker series in data science, Fernando's got to be at the top of your list. And so you've got his bio in front of you. I'll just mention that, Fernando is, well, I should say he's a associate professor at Berkeley in statistics. He's a research scientist at LBNL. He did his PhD in particle physics way he's got a pretty interesting path that he's taken through academia, which I think he'll tell us about. But the one thing I just want to point out is if you ever despair about being in academia and wondering, can I have the impact that I want to have on the rest of the world, Fernando is really just a living example of the tremendous impact and the great good you can do if you do the right things as a professor and as a student. So with that, I think I'll just hand it over to Fernando. Thanks.
Thanks, Mike. Thank you for that kind introduction, and more importantly, for having me here. It's an absolute pleasure. Mike was Berkeley's loss and your win. You have a treasure with him here, and he's leading amazing work. It's been a pleasure to know him and work with him. And some of the work that I'll be talking about here has actually intersected with ways in which I met him. I want to talk a little bit about the bigger picture of open source software in science. I want to credit my co-author. Many of these ideas were developed with Lindsay Hagee, a geophysicist that I work with now in my lab, and a lot of these ideas were kind of refined in conjunction with her work. As Mike mentioned, I had a really bizarre career. I officially hold a PhD in theoretical particle physics by the skin of my teeth. I was fired by my first PhD advisor in my 5th year of grad school. Not a great career move. If you're thinking about grad school, it's not quite the way to do it. I did a postdoc also at CU Boulder in applied mathematics, where I actually did begin using the scientific Python numerical computing stack to do research in PDE methods. That was a lot of fun, and that went well. Realistically, a lot of my time in Colorado was actually spent on the lower right part of that picture, which is really what I probably should have done in the first place. And that's, as we'll come back to later, what I'm trying to do these days. But what happened was, failing at being a proper physicist, sort of being an applied mathematician, but not really, and getting hooked up into all of this writing code thing led to connecting then with neuroscientists because actually of U of C, and we'll get back to that. So I owe my career basically to the University of Chicago in a very real sense that I'll come back to later. But that brought me to Berkeley to work at the brain imaging facility in Berkeley to build open source tools for neuroscience. Then that led to being part of the team with Mike that founded the Berkeley Institute for Data Science with funding from the Moore and Sloan Foundations about 6 years ago, when these ideas were really beginning to gel in academic research. And then as of 2 years ago, I've been faculty in the statistics department at UC Berkeley. So if you see a very weird path, I'm the statistics professor who didn't know what a t-test was when I was hired, and that's not a joke. It's a fact. It's a statement of fact. But somehow one can function in this space through thinking about the role of computers. This is a very old quote from Hamming. Those of you who do signal processing may be familiar with his work. And Hamming was worried in the 60s about the fact that computers were churning on data too quickly for us to reason about it. As you can imagine, any of us in our pockets has more computing power than Hamming ever thought would be possible to access, right? And he was already concerned about that. And that's kind of the space in which I operate. I try to build tools to help us think, to help us reason. But in the spirit that everybody, learning from Bill Howe, that everybody has to have a MATLAB hierarchy slide on their talks, this is how I like to think about open source software, because a lot of people use the word software when they speak about open source, but I think it's really important to consider that the problem goes in two directions, deeper and higher than the software. And it is true that projects such as Jupyter produce software. That is a fact. You can go to GitHub, you can download our code. In practice, what I've learned over the last 20 years or so of doing this, playing this game, is that that's actually the least important part. And a project like Jupyter actually uses that software to provide to the public services and content, and to enable people to communicate with content. And that's actually what people care the most about. Some of the most impactful things we've done with Jupyter and that have really moved the needle on the project have been ways for people to share their thoughts, ways for people to share their work, because code is ultimately a tool. But we've also taken steps that are time-consuming and expensive and delicate and difficult, and we didn't train for, in how to take the ideas that our software has and encode them as more generic ideas that are actually openly specified standards, protocols, things that the community can communicate about, can reason about, can adopt, and that make the distinction between a well-used library and something that founds an entire ecosystem. And then it turns out that stuff doesn't write itself. It's people who do it. It's the meat of this business is the meat of humans, right? We have to do that. And the managing and the fostering and the creation and the healthy nurturing of a community is probably the hardest and yet the most critical part of this whole story. And that's actually some of what I want to talk about. So yes, we do build software. For those of you, these days Jupyter is widely used enough that I'm not going to belabor too much. I'm going to run rather quickly through these things. It began its life as IPython, a terminal-based tool. We have this tool called the Jupyter Notebook that probably many of you have used, which allows you to combine code, text, mathematics, the results of running that code into documents. We also, as I mentioned, run services like NBViewer and Binder are tools that allow you to share your work with others, whether it's to view it or Binder to execute it, let you give someone a URL that actually is either a live viewable or a live executable version of your work with basically no barriers to access. Those have been huge. They've been hugely important and successful because they bring content is what people care about. It's the story about the data, about the problem they're interested in. Now, along the way of building these things, I do want to flag for a moment that we've built a new user interface for Jupyter based on lessons we learned over the years. So the original Notebook web application actually had tools like a terminal emulator and a text editor that are just needed when you're working, say, in the cloud on a remote system on an HPC facility. Over time, what we took was the lessons of why those tools were needed and kind of distilled them into an architecture that allows you to put on a page, yes, Jupyter Notebooks, but also terminals, graphical outputs, LaTeX documents, custom data viewers, 3D visualizers, all of them speaking the underlying protocols that the Jupyter machinery speaks, all of them recomposable. This is something that I just want to flag because I've already had conversations with some of you in this room about the power of this tool. It's a heavily customizable tool. It's a topic for another separate technical seminar that I would love to give one day. It's not a topic for today, but at least I want to make you aware of its existence. We're now almost releasing 2.0 in the next, I think, 2.0 we're on Alpha 2, I think. And importantly, this has been a tool that has been developed jointly between the open source community and industry partners. So Bloomberg and Anaconda have put an enormous amount of work in the building of this tool, and it's part of this story of how these communities get built. Now, moving one layer down in terms of this notion that Jupyter has taken the time to actually distill our ideas in something the community can adopt, I want to flag, just at least for completeness, sort of how to think about the project. And I think it's useful to refer back to the simple, very simplistic, and I know that I am in the middle of people who actually do networking for a living and network protocols. So this is the cartoon version of the web, but the cartoon version of the web that a poor physicist like me understands is that there's a protocol called HTTP, the Hypertext Transport Protocol, and importantly, that protocol is specified, it's documented, it's well-defined, and it's how HTTP servers and clients speak. For most of us, a client is a web browser. That's how mostly you use this thing. You open your web browser for Firefox, Chrome, etc., and you hit a web server. But it's important to know that you're using a protocol because you could be connecting to an HTTP server with a completely different client that has nothing to do with a web browser and to a server that is offering a completely different service over that protocol. Because the point is, once you've specified that transport protocol, then other things on both ends can use it to communicate and build other ideas. That's the value of making. It's not only that there can be more than one browser, even though that is important. Of course, that's important. But it's also that other things can be built and designed. And now, if it turns out that that content is meant for human consumption and there's a notion of a document that we want to view, then we have HTML. We have a way of basically capturing something that is more aimed at the creation of actual documents. And Jupyter has kind of a similar pair. This idea of running code and getting an answer back that began in the terminal that we've had since the dawn of basically of interactive terminals, and Jupyter is basically a souped up version of those ideas. We actually have fleshed it out. There's a Jupyter interactive computing protocol. We have standardized it. We have defined what the payloads are, what the network connections are supposed to be. It happens to be something that carries JSON packets over a 0MQ transport. 0MQ is a networking C++ library that has the advantage that it's basically usable from any programming language, and it's very liberally licensed, and it's very easy and simple to compile and embed. So it's a good low-level kind of piece of machinery, but the point is, that's this notion of I do computing interactively, I send things to be computed, I get answers back. It's effectively like thinking what the simple actions of interactive computing are and documenting every last possible bit of it. It was a simple process to do, but it took some time to refine into something that the community could adopt. And then adjacent to that, there's a document format for how these documents are stored, represented, independent of our implementation, which allows, by having these things, others to build. Because, for example, the protocol, yes, the project began as something that was called IPython. That was basically my PhD procrastination / depression control mechanism. No, in a very real sense, but over time it evolved into something where you could run Julia code. We sat down with the Julia authors at MIT, flew them to Berkeley for a few days, and while we built IPython, they sat on the table next to us, and we began hacking off of that protocol definition how to do this against a Julia engine instead of a Python engine. And then a few days later, one of my postdocs goes to an R meeting, sits down with R people, does the same thing for R. And today, this idea of interactive computing against an arbitrary backend is implemented in well over 100 different backends. And that's the value of taking the time to work with a community to adopt a common standard and a common protocol, of working with those language communities and say, whoa, 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 wait a minute. The way you're describing interactive object exploration is making assumptions about how Python objects work. In our language, it's completely different. The semantics of F# don't support that. How do we generalize that? Now, the trick is you don't have to do 100 of those. You have to do like 2 or 3 well, and then you pretty much are in asymptopia. With these problems, asymptopia starts around 2 to 3. But those first 2 to 3 are heavy-duty, personal conversations, detailed engagements to really understand and think through what is kind of the generalization surface of the problem to do it right. And I think we've been successful in this regard. And as I mentioned, a lot of this is about people. So yes, I started this as a PhD student hiding from my advisor in 2001 in Boulder, Colorado, with IPython. The very original IPython is up on GitHub. It's 250 lines of code, originally GPL'd, and still with the address on GitHub of the particle physics email server, which was Pi0. But none of what we have today would be true if I hadn't had a team to work with and collaborate with. These are pictures of some of our all-hands annual meetings this year and last year in Berkeley and in DC. And what I want to point out is that people in that photograph come from academia. There are people there who work at Netflix. There are people who work at IBM, at Bloomberg, at Anaconda, at Amazon, at Netflix, independent consultants at national labs, startups in Europe, government research labs in Norway. So it's a very heterogeneous mix of people from academia, from industry, from research, all working together towards a common goal based on this notion that we have a neutral space where we're creating things for everyone to share. And engineering that takes a lot of effort. Mike did a lot of that work at Berkeley with the successful AMP and RISE projects. And we've spent time learning from them and learning how to do this in this intermediate space between research, tool creation, industry interests. And it's tricky. It requires that you do things like formalize your governance processes. Who here, as part of their PhD in computer science or chemistry or physics, has had a course on organizational governance? Yes, that's the hardest part of this project. That is by far the most challenging and most difficult part of this. We've had to actually engineer the human mechanisms for maintaining a healthy collaboration between universities and the biggest tech companies in the world, between engaging in a meaningful way between all of these actors, how to fund this work, how to have actual proper bylaws and rules and processes to do that. And that actually, if you don't do that, the code does not write itself. The community doesn't grow by itself. All of these impacts don't just happen because you're very smart and have a GitHub account. That's not how it works. Now, I want to very briefly flag something about the value of these tools in education. We don't have time. This would be, again, the topic for a whole nother talk. But we have been building a very large data science effort at UC Berkeley that is made possible by these tools. So the picture at the top is the opening day of classes a year ago in the fall for our Introduction to Data Science course called Foundations of Data Science, Data 8. That is not a classroom, by the way. If any of you have been at Berkeley, that's the Opera House. That's basically the campus performance hall. It's the only place on campus that fits 2,000 people. And so we have to borrow it. We're not allowed to lecture there. They're not going to let you lecture for a whole semester in there. The students would trash it. But we're allowed to use it for the first day to have the opening lecture of Data 8, which has about 1,500 students. I think now there were 1,300 that day. And then we have to tell them not to come to class, because the bottom is Wheeler Hall, which is the biggest actual lecture hall on campus, and it only fits 750, which, as you will notice, is a number lower than 1,300. And that's the physical capacity of the largest classroom on campus. So we have to tell them, watch the lectures on average on YouTube. Don't come in person to class. But by having built, obviously, content, obviously by having built material, and having this infrastructure of open source tools that are deployed via Jupyter through the web browser in the cloud, then we can reach this volume of students. And we're basically now transforming the campus. We have very broad disciplinary reach. Those students come from every major. Those are not CS and stats students. They're students from every major. They're freshmen who arrived on campus a few days prior, right? So these are kids who were in high school 3 months earlier. We lower the barriers, both intellectual and technical and economic. Any student who doesn't have a laptop, whose laptop breaks down and can't afford to buy a new one, walks into the library, borrows a Chromebook, and they're back up and running in 30 seconds, right? And they can keep that Chromebook checked out from the library for the entire duration of the semester. So there's no issue of do you have the best resources, do you have the fanciest laptop, or do you come from a poor family and can't afford it? That issue is just completely taken out of the equation. And we also lower, very importantly, the barriers to faculty to do these kinds of work. Those courses are taught by computer science and statistics faculty, but those courses are just the backbone of a constellation of other courses that bring data ideas into the curriculum that are taught by faculty from all departments. Those faculty would never have people in linguistics, in sociology, in multiple domains who don't have the need or the infrastructure to run a computationally heavy course, but they have the domain expertise of their field. They can develop those ideas in conjunction with students and an organization that helps them actually put that content on that infrastructure that already exists and add these ideas onto their courses. And that has been absolutely transformative at Berkeley, because now the impact of these courses goes basically to every department, to every discipline, not just through the students, but also through the faculty. So we kind of come at both ends. The students from all campuses are taking these baseline courses, and the faculty from all departments can participate in the creation of these kinds of courses that have data-intensive bits and pieces in them, even in existing courses. Not just build like new data science courses, which also happens, but actually add this kind of content to the existing courses. And that is the value of having this on this shared, commonly built and accessible to everyone infrastructure. Because everybody with a Berkeley ID can go to datahub.berkeley.edu, and they're logging into one of these Jupyter Hub things in the cloud. Now, we're not teaching them to be Olympic cyclists on a tricycle, right? We are teaching them with real tools. These students are learning with the tools of research. And so what we put them in front of are the tools that make it possible for us to hopefully embody what folks like Buckheit and Donahoe were saying over 20 years ago about research, which is that we shouldn't be sharing PDFs of papers. That's perfectly fine to tick a checkbox on your CV, but that if you actually want to share the real work that you did so others can build upon it, you need to go a little bit further. That argument was made over 20 years ago, and they were effectively channeling John Claerbout, a geophysicist at Stanford. And today we've built the tools that make that possible. So Binder is a project that began out of Jeremy Freeman's lab, a neuroscientist who actually used to work with Mike on using Spark for neuroscience. He's now at Chen Zuckerberg. And what Binder does is it's a tool built on the Jupyter machinery that says, if you give me a Git repository, typically on GitHub, but it doesn't have to be, but if you give me a Git repository that follows good practices, where you have your analysis code well organized in notebooks, and importantly, you tell me how to run it. You give me a list of the libraries your code needs, or the dependencies your code needs, or the Docker file, and there's many ways to do that. But basically, if you do the right thing of organizing your code and stating your dependencies, we'll take care of it. Because we'll pick up that description, we will compile it into a Docker image, we will deploy it on top using Kubernetes in the cloud, and we will give you back a link, which is a live executable version of that thing, no matter how ugly and monstrous it may be. So it doesn't have to be like nice 2 Python packages that use NumPy and Matplotlib. It could be some god-awful piece of C++ and Fortran that requires boost and a build of GCC from last night at 3 in the morning. If you manage to build the darn thing and shove it into a Docker image, you can give it to the world. And in 2015, you may have heard that something went poof in the night. Right? The 2 black holes merged about 1.3 billion light years away, and the outcome of that merger produced a ripple in space-time that was detected as a gravitational wave. This made a lot of waves in the news. And led to the 2017 Nobel Prize in Physics. This is the first figure from the main paper of the LIGO detection of that first event of the merger of a binary black hole system. It's probably going to be one of the most cited papers in physics for the next few decades. That entire figure was made with the open source scientific Python stack. So all of that analysis is done with NumPy. The plots are made with Matplotlib. The analysis uses NumPy, SciPy, the rest of the scientific Python stack. The color map used at the bottom to display the images is Viridis, which was developed by a team at Berkeley at the Data Science Institute to have much better perceptual properties. This was kind of a dream come true for us. 15 years earlier, we were arguing like crazies in the desert that yes, this Python thing is real and we can do science with it. And the most important result of the last decade in physics was achieved with these tools. The team behind the LIGO project that did this, oh, and I should have checked. I don't know. This is, we'll see if we have audio. We'll see. Published the Jupyter notebooks that produce all of that analysis. And you can go to that URL and run them yourself. So if you go to that URL, or if you go to the LIGO Open Science Center, you'll find a link. You click on that link, and you're loaded into a binder hosting the analysis notebooks, the code, the data, the library, so that anyone from the general public can literally run the analysis, play with the parameters. Now, not everyone needs to do that, but the point is that it is possible. The point is that you have access to the code, you have access to the data. And you can hear that. So that's the last in spiraling that lasts about a quarter of a second of 2 black holes that weigh a total of about 30 solar masses colliding into one another 1.3 billion light years away. And you can listen to that by just hitting click on a binder URL. I think that's kind of cool. So the other big event in physics recently was this one. You also probably saw it in the news. This is, for those of you who were very deep asleep for those entire few weeks, was the first direct image of a black hole, of an actual black hole, or the event horizon of a black hole, taken by the Event Horizon Telescope. The physics and astronomy people at Berkeley were very savvy in that they engineered that Shep Doleman, who's the director of the project, and Katie Bauman, who's one of the lead scientists on the imaging side, would give the very first public lectures the day after the press releases came out, were at Berkeley in the physics and computer science departments. And well, I couldn't see Katie's talk because by the time I made it to the lecture hall half an hour early, the fire marshals were already kicking people out because it was already in overflow mode. So I got to see it from outside screens. I did get to see Shep's. This is one of the papers in the main series of papers that came out that day when they pushed them out. And it is citing NumPy, SciPy, Pandas, AstroPy, Jupyter, and Matplotlib. So they actually cited the entire scientific open source stack. If you want to get a really good data science talk. Now, Katie is now faculty at Caltech, so it's a bit of a trip. Her talk on the construction of that image is a work of art of data science because the construction of that image is a statistical problem. That image is taken by radio telescope, so what you get is Fourier domain data. If you take that inverse Fourier transform, you end up with a completely messy blur that provides exactly 0. How they constructed that image, the statistical modeling that went into that, the validation of the various modeling approaches, combining both traditional techniques used by the radio astronomy community that were very, very model specific, and much more sort of ML statistical Bayesian techniques, and how to compare, contrast, and validate those is really one of the most fascinating pieces of modern data science that I've seen. Now, in geosciences, at Berkeley, Lindsay Hagee is working on building tools that bridge, use the power of this machinery to go from numerical computing in geophysics. So her specialty is inverse problems, basically trying to image the subsurface with electromagnetic current data and then solving the inverse problem, which means you have to solve a forward simulation with Maxwell's equation and an optimization problem with inverse data, and how to use those techniques to actually teach geophysics to build interactive, Jupyter-powered documentation, interactive exploration tutorials, computationally driven widgets and elements that actually teach geophysics off of those same research codes, and building a community, the community of scientists that used to be, this is a world that used to be dominated basically by the oil and gas industry, so highly proprietary, highly closed tools, and how to basically break that entire scientific discipline open. She recently won kind of the major early career award in her field by building an academic career purely off of these kind of this open philosophy, all the way from numerical computing down to education. And that takes me to the fact that we are investing in my group more of our time and effort in the direction of the geosciences. This is a project that is built upon Jupyter called PanGeo, originally led by Ryan Abernathy, who's an oceanographer at Columbia University, and Joe Hammond, who's a hydrologist and climate scientist at NCAR Boulder, though Joe physically lives in Seattle. And what Joe and Ryan asked was the question of what are really the bottlenecks in the climate and earth sciences community today that are breaking down what should be the virtuous cycle between theory, computational modeling, and experimental data, and the feedback between those areas of the discipline. Why is that not working as well as it should? And their answer was people are basically falling on their face on the technical complexities of the data management, of data access, of visualization, of exploring, of connecting a simulation run to the actual observations, even though, sure, the codes scale and they get put on the supercomputers and they run a 5 million core hour bill for DOE or NSF or NCAR, but then what science do you get out of that? And they said what's breaking down is really the tool chain, and actually the open source world has a bunch of good stuff for that. What's missing is assembly, is final deployment for a domain. So the PanGeo project takes a Jupyter front end, a Dask distributed computing engine, an X-array data, basically n-dimensional numerical arrays with rich physical sciences metadata, and gives you tools that let a scientist do something like that. I need to zoom on an image. Well, zoom on an image. Wait a few seconds. Oh, the image got sharper. What's the big deal? We all do that. Like you zoom on an image and there's a little bit of lag and then you get a better zoom after a second. Well, the point is zooming on that image requires zooming on 100 gigabytes of satellite imagery that cover the entire state of Washington, which can only be processed by a distributed cluster. For a scientist to do that, they would normally have to basically become a cloud engineer and kind of rig the entire machinery to be able to do that interactively. With PanGeo, they just put their image on the cloud. The little color bars at the bottom that flicker while you do this, that's the Dask cluster. Those are the nodes on the cluster that are basically kicking into gear so that the zooming can be done interactively, and they begin allocating jobs and kind of doing the various pieces so that you can get an image. And that's the point, that you shouldn't, as a climate scientist, you shouldn't have to become an Amazon engineer. You should just zoom on your data, and something should do that job for you. And that's the point of PanGeo. And off of PanGeo, with Joe, we just got an NSF grant funded. We had our kickoff last week called Jupyter Meets the Earth, where we're now taking 3 domain use cases: Joe's climate data analysis case, Lindsay's geophysics use case, and Laurel Lawson, who's a hydrologist at UC Berkeley, as 3 scientific domain drivers for developments in the Jupyter ecosystem. And this is an important milestone for us because it is the first time, first of all, because I'm kind of focusing most of my effort now in the geosciences, but importantly because it's the first time that I know of that the federal agency really dedicates funding in a kind of software-first case to these kinds of community-driven open source projects together with the science. But we didn't hide, right? We didn't do any of the wink, wink, nod, nod. We're going to do science and software is magically going to appear because we're not going to talk about what the grad students and postdocs are actually doing. No, we actually put the software next to the domain science, and the NSF was happy to do that. And that has been very hard in the past. So we're very happy about this. Now, as a matter of completeness, yes, all of these tools are heavily used by industry these days. Amazon, Microsoft, IBM, Google, they all have, not just they use it, but they have products based on Jupyter and on these tools. But it is important to think of the fact that these companies have a combined value in the multi-trillions of dollars, right? And this ecosystem is in a very, very brittle state of sustainability, and that's what I want to get a little bit more into. Because it has been funded, and we have received funding, some funding from private foundations, a little bit from DOE, and now the NSF. But largely, this has happened because of these few private funders that believed in this when no one else would, and because of industry, and because of a lot of people gambling their career in odd ways. Because normally, if you say that you want to build data science tools in academia, So Matplotlib, the data visualization tool that many of us use in Python, was actually created here at U of C. NumPy was created by a professor at Brigham Young. And Sage, which is a mathematical open source platform, was created by a mathematician who's now faculty at the University of Washington. When Travis Oliphant, the creator of NumPy, went for tenure, his department was like, NumPy? Is that really any useful for anything? We don't know. Why don't you go back and write more papers and reapply for tenure in a few years? At that point, he said, screw that. I'm out of here. Went to industry. Matplotlib was created at U of C. At the pediatric hospital here, they were studying, John Hunter had done his PhD here, and he was studying children with severe epilepsy who were subject to a surgery where their basically skull cap is popped off, and electrode patches are put on their brains to record electrical activity data. And he wanted to build, instead of using that tool, which was a expensive $10,000 dongle-activated proprietary software, he wanted to do that in Python. And so he built Matplotlib as a tool for that kind of work. But a few years later, there was no way for him to have a livable career in academia that way, and left to work at TradeLink, which is a hedge fund in downtown, here in downtown. Now, when I say that I have my career thanks to U of C, it's because it was my connection to John that led to me connecting with the team at Berkeley that gave me my first job at Berkeley. So there's a very direct connection for me between U of C and the rest of my career today. But basically, John had to go into a hedge fund instead. William Stein, PhD at Berkeley, postdoc at Harvard, straight up to a tenure job at UCSD, straight out of a postdoc tenured appointment at UC San Diego, now full professor at UW, and he wrote a few months ago this blog post that basically said, I can't keep doing this open source stuff. I'm trying to build a company to sustain it so that we have some revenue to keep paying the open source developers. This is not working. I have decided to resign my position. And this is a guy who's probably one of the most respected number theorists of his generation today in number theory and crypto. A guy with a gold-plated academic CV. So scientific open source has largely happened despite sort of official support from the structures that kind of give us support. Unfortunately, a lot of the funding that goes into scientific software infrastructure suffers from this perverse vice of go build the new shiny thing, right, rather than work with anything that actually gets the job done. It's not about getting the job done, it's about the new shiny thing. There's two keywords that those of you who haven't yet had the pleasure of writing an NSF grant will eventually become very familiar with. They are the word novel and the word transformative. Right? Those two stupid words are the most poisonous piece of information that has ever been injected into the federal funding system, because they justify the stupidity of this kind of stuff happening over and over and over, and literally billions of dollars have been sacrificed on the altar of those two stupid words. The Pangeo project is an exception. They said, we're not doing that. The road almost gets us there. We're just going to finish finish that last bit of pavement. We're going to do it, and then we're going to straighten a couple of the curves that are a little bit ugly, and we'll do it for a fraction of the cost, and everybody will be getting there tomorrow. And that's exactly what they did. I did say this to the NSF a few weeks ago, and they were receptive. I think the problem is that the novel and transformative nonsense is courtesy of Congress, so I think that one's hard to remove. This is the problem. On any dimension that you look at, the creation and construction of these open collaborative tools and ideas is at odds with the incentive mechanisms that we have throughout the system, from academic hiring and promotion and publishing and tenure to grant writing to awards, etc. On almost, and I could basically speak for 20 minutes on across the grid of this slide, which I will not do so that we have a little bit of time for conversation. But the point is that on each of these dimensions, I think this model can be healthier and more productive and more effective and deliver actually more value both to individuals and to society. But we've managed to engineer a system of incentives that makes exactly the right things the hardest things to do, and that's a problem. I want to concentrate on the fact that things are, it's not all doom and gloom, by the way. Things are getting better. And in particular, over the years, we've built all of this stack that takes Python and then has kind of general purpose tools like NumPy and IPython and SciPy and Matplotlib, a little bit more specialized ones, but still kind of broad spectrum tools like scikit-learn or scikit-image, and all the way to very domain-specific things like SunPy is a tool for solar physics, right? Very, very specific domain application. And of those, there's many, many more. In the domains, obviously, you have as many tools as there are sort of disciplinary endeavors. Ignoring Python for a minute, that's kind of, other people do that. We can talk about that if someone's interesting, but I'm not going to focus on it for now. But these two rings of what I call the domain agnostic backbone, right? The kind of somewhat generic tools, that's the space where I spend most of my time. And it's not real computer science. It's not real research. It's basically nobody's problem, right? That stuff is basically nobody's problem. It's the stuff that gives no one credit, that gives no one a career, that no one wants to fund. Guess what? You can't build the rest without it, right? You can't build the rest without it. And it's very tricky to find ways of justifying, and I'm being, obviously for theatrical effect, a bit exaggerated. We have gotten funding, we have gotten grants, I do have a job. It's not all doom and gloom, right? But it has been very hard. I got my PhD in 2002, okay, and I got my job in 2017. So 15 years is not exactly a career plan that anyone should realistically consider. Now, this is not a new question, a new problem. There's a bunch of organizations trying to help here in the direction of teaching people across kind of some of the skills that are needed to do this work better, whether it's in software or data management. The Carpentries is a fantastic organization that teaches kind of short, focused workshops. In terms of the question of what are the realistic career paths for people with a scientific training, but who would like to spend their time kind of closer to the code, because that's what they enjoy doing, that's what they like to do, there's a movement called the research software engineering career path that really began in the UK and is very well organized in the UK, and now there are people being hired as RSEs. Recently there was the first faculty hire. Simon Hetrick got a faculty position at USav Southampton, fully tenured, as an RSE. And they hired him to say, you should come as a research software engineer professor. And so this is beginning to change, but they recently opened up a US chapter and they have kind of a US presence now. And I think it's a really interesting development from a professional perspective. Hold on. In 2012, actually with John Hunter and Travis Oliphant and a couple of other people, 5 of us co-founded an organization that now is led by much better people than us and has grown a lot, called NumFocus, which is an actual nonprofit, a standard 501c3, that helps basically bridge between these distributed open source communities, the academic world and the industry world, and provides things like legal services and fiscal sponsorship, and also a bunch of other really interesting initiatives in diversity and better community management for a lot of the scientifically focused packages. So it's not just about like free software in general, which is a perfectly fine thing to worry about, but that's a separate problem. It's about open source software in science. Mozilla, the people who make Firefox, they actually run really interesting efforts around organizational leadership and management. And that is really extremely valuable. We've had folks from Jupyter participate in some of their trainings, and they're a very interesting organization that is basically working on the problem of leadership in open heterogeneous communities and doing some really good work there. The problem of getting academic credit for things like open source software or open source educational content is a really important one. And two efforts, so Kate here works on a project connected to that. And there are two folks in our community, Lorena Barba, who's faculty at George Washington, and Arfin Smith, who is at the Space Telescope at Johns Hopkins. Both lead the Journal of Open Source Software and the Journal of Open Source Education, which basically allow you to get effectively academic credit and for software or educational artifacts that have been developed in the open, but in kind of the atomic unit that people know how to count in a more academic context. But with minimal effort, it's actually a really well thought out model. This notion of connecting training, but not in a bootcampy sense, but actually to the research questions of a discipline, and building a community that develops ideas around research problems in a discipline while learning how to build is something that around this more lone effort in data science, a little pattern emerged, and they're called Hack Weeks. It began with Astro Hack Week, but now there's Geo Hack Week, Ocean Hack Week, ISAT Hack Week. The neuroscience one got big enough that now it's called Neuro Academy because of the last 2 weeks. And the idea of these events is to basically connect a group of people from undergrads to senior PIs with a lot of attention paid to how to engineer that community to work for a week or two on both learning skills and actually hacking on things, building new projects, testing new ideas that may lead to papers, to new research projects, to collaborations, to new tools being developed. It has been a phenomenally successful model. The team that leads these actually wrote a paper on PNAS that I encourage anyone interested in education and community to read that paper. It's a really well thought out reflection on how the human and social engineering behind these things needs to be done. And for example, the ISAT2 one was phenomenal. I participated, I taught in it, and it was so much fun that I got together with the organizers, and we just put this last week, a new NASA grant proposal that we wrote last week on developing open source Python tools for analyzing data from ISAT2, which is it's a LiDAR instrument that NASA just sent up to monitor ice on Earth, polar regions, mountain ice, etc. So fundamentally, even though these organizations exist, and I wanted to kind of give credit to the existence of these efforts, what we have is an economic problem, an organizational problem that isn't fully solved. We're victims of what Tracy Teal from the Carpentries, I think, very aptly calls catastrophic success. A paper came out a few years ago looking at the role of IDL, which was the most heavily used proprietary tool in astronomy, compared to Python. And by 2015, Python was by and large basically wiping IDL out of existence. Well, it turns out that IDL or Mathematica or MATLAB are companies that employ thousands of people. Those thousands of people actually did a job. Okay, they actually did useful things like writing good code and documenting it and fixing bugs in it. Yes, it was closed source. Yes, it was proprietary. But they weren't just sitting there collecting rent for nothing. Who is going to do if we are saying that the scientific backbone of Event Horizon Telescope, of LIGO, of every project funded by NSF, DOE, DOD, NIH, etc., is all going to be done on open source software, where's the work of those people? Who's paying for that work? Who's going to sustain all that? This is a problem of strategic risk. And if you want to have a seat at the table of managing that risk, you have to invest. You have to put resources into the problem. Because if not, that space is going to get filled up strictly by the commercial interests who do see value in these things, who are actually developing also open source tools, but open source tools as a strategic control asset, TensorFlow, PyTorch, etc., are tools of basically the strategic battle around machine learning on the planet from the richest companies on Earth, and as engineering recruitment tools. They're not building those tools for the greater good of an open, multi-stakeholder, interoperable community. They're building those things for themselves. So if we want a voice in the development of these things, the scientific community and the funders of the scientific community have to actually invest, because you get a voice at the table by participating, not simply by saying that you should have a voice. I think there's a lot of bang to be had for the buck here. The federal R&D budget is of the order of $200 billion, give or take. 0.1% of that is $200 million per year. 0.1%. Do you think 0.1% of research today involves computers? Or maybe a little bit more than 0.1%, right? How much of research involves computers today in an important way? 30%, 50%, 70%? I don't know, but a lot. It's not 0.1%. If we devoted 0.1%, we'd be spending $200 million on core open source scientific software infrastructure. That would already go a long way. But the trick is we have to spend it well. And this is an interesting problem. I don't have all the answers. I have some ideas. I've thought a lot about it. It's an interesting problem of organizations. It's an interesting problem of incentives. We need to recognize that open source projects are real, complex human organizations that live in a very interesting intersection of spaces and interests, right? And understand what are the ones that work well, what do they do well, what have they done, how can we nurture them, how can we nurture that without killing creativity, without killing innovation? How can we do it in a way that is actually more inclusive? Guess what? The notion that volunteers are going to do this job is a great way to make sure that only people who can afford to volunteer do the job, which means typically less women and minorities, because they tend not to have the freedom of spending their nights and weekends doing this, because maybe they have to have a second job, maybe they have to take care of their families. So if you want to actually bring other people to the table, you have to recognize that this is a job. This is not just us. I had a quick look, and in the last week, 4 different blog posts attacking different angles of this question very thoughtfully have been posted. These mostly are more about kind of the web/industry side of open source, a little bit less about science, but a lot of the same questions and reflections apply. This quote from the bottom is from Matthew Garrett. He's an old, kind of an old Linux contributor, very core Linux guy. But that statement is exactly what we've been talking about, right? These projects that are critical to the most important scientific results of the day are chronically underfunded and have effectively no sustainability path. I recommend anyone interested in this that you read this report. It was written by Nadia Agbal. She's an engineer at Protocol Labs. This was paid for by the Ford Foundation. It's a really well done report on thinking about open source as infrastructure. In her case, not, again, more on the industry than the science side. It's a brilliant piece of background research on this topic. And Nadia has been thinking a lot about basically how to tackle this problem creatively, referring to work from people like Elinor Ostrom, Nobel Prize winner, who did a ton of work on studying how sustainable communities govern common resources. A lot of her work was done around water resource management and watersheds in California in the 70s. I think she died in 2009 or so, but her work is kind of one of the foundational pieces of theory around this. So I'm going to try to leave a few minutes to chat, but my main message is that there's a lot more than software to open source. And I think some of the yes, we're doing great work that is changing education, it's changing research, it's changing how the conduct of science, but we need to think about the role of our tools and how we build them if we want this to continue along at the very least these dimensions and a few more. I'm going to thank my colleagues in the Bay Area, because Jupyter is an international project, but these are the people that I spend most of my time sort of close by in the Bay Area, and without them, none of this would exist. And I'm going to leave by dedicating this lecture to John Hunter, the person that I mentioned, who sadly passed away in 2012. He died very young, leaving 3 daughters. He had left UFC, but about 7 years to the day today, I was giving his eulogy at Rockefeller Chapel, so I was here kind of with his family. He fell ill right after the 2012 SciPy conference and passed away in 3 weeks. He was my best friend, and I literally not only wouldn't have this career, but we probably wouldn't have the scientific Python ecosystem that we have today if it hadn't been for his work that began here at UChicago. So thank you very much for your attention.
So I'm interested in your thoughts at Berkeley on how you have worked to help bring computing and statistical training to people in the sciences outside of computer science. So that is something there seems to be a huge need for. My group ran a series of boot camps in September. We had 130 signups in 1 week from grad students trying to get extra training. And we had these heart-rending little stories in their reasons for signing up, like, I'm a third-year PhD student in physics and I've never had a statistics class and I don't feel qualified to work on my own PhD research. So how do we overcome that, especially when students have a heavy course load already?
So the model that we've used, and it's not perfect, and there's still a lot we can do, and now that I have kind of an actual educational mandate, I hope to contribute to that, but there have been a few bright spots. Starting about 6-7 years ago with a colleague called Josh Bloom, we started teaching actually also a 3-day boot camp. He really led the development of that, but I worked a lot with him on teaching those. These were 3-day boot camps that were taught at the beginning of a semester, and the idea was, if you were, and many postdocs took them, some faculty came, some staff came, but if you were a student, you could then sign up and stay for an elective course called Astronomy 250, but it was really called Python for Data Science. So Josh would teach then a semester-long course. So people could choose to either just take the boot camp, which honestly was so intense that it was basically, this is what you should learn later, because nobody could really absorb in 3 days that much, but at least they got kind of the basics, and then the people who really wanted to learn it would sign up for his course. And that was a really interesting and valuable combination, kind of boot camp followed up with an actual in-depth course. Now the physics department offers a course called Data Science for Physics, taught by, he's a cosmologist, Ur Selyak. Very, very good materials. They actually got a grant to kind of refine and polish that course. I've been teaching myself some stats out of it, honestly, because he's really done a very good job with the development of those materials. And those are now beginning to emerge, because what's happening is the existence of these foundational courses, these backbone courses like Data 8, is allowing the growth of what is called the system of connectors. And the connectors are courses that can assume that people have that basic backbone on very basic inference, data analysis, visualization, and simple programming, and then they can go a little bit deeper into their discipline. So for example, there is a course taught right now by Nick Swanson-Heisel called PyEarth, which is basically data science for earth sciences, and he can assume that the students took Data 8, so then he goes a little bit deeper into issues around earth sciences.
Do you have open curriculum philosophy, just like you have open?
Yes, all of those materials are open. The only thing that's not open are the video lectures because of an issue with accessibility. We're not allowed, but everything else is open. Mike.
I was just wondering if you could say a little bit about sort of what were the keys to the success of IPython and Jupyter in terms of adoption. I mean, like you said, you don't just put out a GitHub and things take off. So, I mean, what are the key things that you need to do?
Yeah, so obviously, this is a very highly biased take from my own history, but I think a few factors played a role. One was we were really using it. We weren't building something just on some external mandate, but make me a thing that does these things. At the beginning, it was me, but quickly others. The people, and if we look back at the archives, the people on the IPython mailing list from early on were working scientists who were adding features, sending feedback from, really it was kind of the eat your own dog food from day one. Right? And that was true. John needed Matplotlib for his work. Travis was working on the predecessor to NumPy and SciPy as a medical imaging postdoc. Eric Jones had founded a company to sell scientific Python tools to industry. And so there was this notion that we were building, first we were solving a problem, right? Second, there was something about a community that was very willing to collaborate. To give you an example, we met in 2005 because of that neuroscience thing, and we got together at Berkeley, a few of us, John and Eric and Travis and I and a few others, and we realized, look, IPython is about interactive computing. It has a bunch of numerical utilities and a bunch of plotting stuff. SciPy is an algorithms toolbox that has a visualization component and a shell. Matplotlib is a plotting library that has a shell and that has a numerical utilities libraries. Let's just diagonalize this matrix, right? This confusion matrix is leaking. Let's diagonalize this thing. And IPython does interactivity, SciPy does algorithms, and Matplotlib at this point. And we were willing to just literally move code around and share it. There was a sense of trust and willingness. In fact, IPython early on was GPL. That's what I had done. And John said, hey, as long as you give it GPL, we can't copy and paste. We're not allowed to copy and paste. Like, all right, let's just change that license so that literally we can move the code into the right places. And there was no sense of we need to fight for credit here. There was a sense of what's the right thing to do, and let's just do the right thing. And then I think there was just the luck of good timing, right? There was a pressure of timing. The web was growing. The tools for collaboration in open source were growing. And the desire for open tools was growing. And so we kind of rode. I think we did a few of these things well. And we rode a good wave of timing. And I think the combination of those two things helped a lot. Question?
So you showed these 4 layers, starting from Python and then going to these specialized libraries for astronomy and all other disciplines. So I was curious, like in your opinion, what is currently the biggest need in these 2 layers? Yes, between Python language and then domain-specific libraries. So these core and specialized libraries. So you also mentioned that there is maybe some threat from companies such as Facebook and Google. They have these specialized frameworks, as also we discussed yesterday, such as PyTorch or TensorFlow. And I was thinking, for example, if we could create something like wrappers around these frameworks to, let's say, expose NumPy-like interface to these libraries. And like for you, first question is really like, what are the biggest needs in these core and specialized layers? And then, what are really these threats from these companies that create these specialized frameworks, mostly for their own needs?
I mean, so on the needs side, I would say that the big thing that companies like Mathematica and IDL and MathWorks can provide, right, is really seamlessness of and integration. And that is missing. You can assemble this tool chain, but there are pieces where the seams show in unnecessary ways. There's friction in between the tools that is unnecessary. It took a long time for scikit-learn, for example, to recognize how to handle a data frame. The type representation between NumPy and pandas is kind of weirdly incompatible at a low level. Now, those teams are trying to talk together, but if now we ask the question of where could these entities contribute a little bit more, I honestly would love it if they were willing to put more resources into building common ground rather than kind of building their own thing. So for example, a fraction of the development resources that Google and Facebook together have put into TensorFlow and PyTorch is orders of magnitude what this entire ecosystem has ever had. A fraction of that could go a long way to improving those common layers. So for example, understanding what are the commonalities in tensor machinery, tensor management machinery that we need, and what improvements can go to the bottom, even if they continue doing some of their own thing with their hardware and their infrastructure and their needs. And there's a little bit of that happening, and actually at Berkeley they're beginning to organize an event around some of that will probably happen in a few months, but not enough. How to convince these actors to do more of that? I mean, we talked to some of them, but there's a limit to the battles I can fight.
Okay, I think that's all the time we have. But thank you very much for a brilliant talk.
Thank you so much.
Just to remind folks, next week we'll have both the seed grant proposers day, and next Friday there'll be a talk on machine learning for security.
I'm in
Oh, I want to hear. Hey, Liz, there's a workshop.
I actually have its own problem.
I'll send you. I'll send this to you. They're looking for teams to.
They want people to be
yeah.
saying not like you.